Hi, in this video we are going to talk about the second most important graph traversal algorithm, the so-called depth-first search or DFS. So, let's get started. Depth-first search is a widely used graph traversal algorithm besides breadth-first search. We have already discussed breadth-first search in the previous section. It was investigated as strategy for solving mazes by Tremo in the 19th century. It explores as far as possible along each branch before backtracking, and basically that's the most important difference between breadth-first search and depth-first search, because if you may recall, the breadth-first search was a layer-by-layer algorithm. So breadth-first search, or BFS, is going to visit the neighbors first. Here, for DFS, depth-first search, it explores as far as possible. So maybe it's going to visit the furthest vertex before it visits its neighbor. So okay, that's the main difference between depth-first search and breadth-first search. The time complexity, on the other hand, is the same. Ordo V plus E, where the V denotes the number of vertices, the E denotes the number of edges. So it is linear as far as the number of vertices are concerned. It's very important that the memory complexity is a bit better than that of breadth-first search. We have been discussing that breadth-first search sometimes is very useful, but the memory complexity is not that good. Depth-first search, on the other hand, a bit more memory friendly. Okay. So let's see the pseudocode. Unlike breadth-first search, depth-first search can be implemented with the help of iteration or with the help of recursion. As far as I am concerned, the recursive approach is a bit better because it's more compact. By the way, in the background, the operating system is going to use a stack abstract data type no matter what. We could use recursion, a stack will be used, or we could use iteration, and in this situation we have to define this stack, but the result will be the same. By the way, if you are interested that as far as the performance is concerned, the recursive and the iterative approach is approximately the same as far as performance is concerned. So the depth-first search is not going to be faster if you implemented it with the help of recursion. It's going to be the same approximately. So what about the iterative approach? We have to define a LIFO structure, a last in, first out data type. This is the stack. So we have to create a stack, we have to set the starting vertex to be visited, and we have to push it to the stack. And then while the stack is not empty, we pop the item from the stack, we visit all the neighbors of this item, and if it's not visited, we set it to be visited, and we push it to the stack. The implementation is very similar to that of the breadth-first search implementation, but instead of using queue as an abstract data type, we have to use a stack. And it is a very common interview question, that what's the difference as far as implementation is concerned between depth-first search and breadth-first search. And basically it is the abstract data type. For depth-first search we have to use stacks. For breadth-first search, we have to use queues. So let's see a concrete implementation. We start at the root node, so with the A, and we keep visiting its children. So we visit, for example, the left child. It's very important, then we could visit the right child as well, so it is quite symmetric. In my implementation, it's going to be the left child that we visit first. And instead of visiting all the neighbors of the root node, we keep calling this method recursively and we keep visiting its neighbors. So we keep visit the neighbors of B. And we come to the conclusion, this situation, that it doesn't have any children, so this is the so-called backtrack phase. We have to go back to the parent node and check whether are there any unvisited children. And yeah, we come to the conclusion that the right child is unvisited. Again, we pose the question that are there any unvisited neighbor? Yeah, the E. In this situation, the E doesn't have any children, so we backtrack to the parent. It doesn't have any unvisited children, so we backtrack to the parent. Okay, the B has 2 children, the C and the D, but we have already visited it. So we backtrack to the parent. We visit the F because we haven't visited it. Then we backtrack to the A because the F doesn't have any children. We visit the right child, the G, and we visit its children, the H. Here we come to the conclusion that it doesn't have any children, so we backtrack to the parent. The G doesn't have any unvisited children. Okay, it has a left child, but we have already visited it, so we backtrack to the parent. And when we come to the conclusion that there are no unvisited children for the root node, we consider that we have finished. There is no unvisited vertices for the starting vertex. It means that we are done. So what are the applications of DFS? For example, topological ordering. We are going to talk a lot more about topological ordering, so I'm not going to talk about it now. But for example, the Kosharayu algorithm for finding strongly connected components in a graph relies heavily on depth first search, and it can prove to be very important in recommendation systems such as YouTube. I'm sure that you have the situation when you were watching some videos on YouTube and it's going to recommend some videos as well. And basically, in the background, we could use the Kosharayu algorithms and strongly connected components, which relies heavily on depth first search. So basically, you may have the intuition, as I had a few years ago, that algorithms and data structures have absolutely no use. But no, quite on the contrary, in the lowest level, most of the times, there are these kinds of algorithms that's going to be used on a daily basis. Okay, we don't have to know about it. We don't have to implement it from scratch because Java has already have an implementation. C++ has already have an implementation. But I think that it's good to know the theoretical background for these kinds of algorithms. Then another application for depth first search is detecting cycles, checking whether a graph is a DAG or not. What does it mean, DAG? It means directed acyclic graph. So a graph that doesn't contain any cycle and it is directed, it is called a directed acyclic graph. It is devoid any cycles. And it's very important in operating systems. We have several processes, and sometimes we bump into the situation when a process is waiting for another and the other process is waiting for the first one. So basically there's a cycle, and if there's a cycle, then the operating system is going to freeze. And this is why these algorithms are very handy, because we can check at runtime whether there is a cycle or not, and we can eliminate these kind of operating system freezes. Okay, and for example, if we would like to generate mazes, or we would like to find a way out of a maze. This is what I have been talking about at the first slide, that this is why depth first search came to be. This is the so-called Tremo algorithm that's going to find a way out of the maze. So just to be clear, breadth first search is going to visit the nodes on a layer by layer basis. We visit the root node and then all the children of this node, so the second layer, then all the children of the root children, so the third layer, then the fourth layer, and so on. On the other hand, depth first search is going to go as deep as possible on a single branch. And it's very important that it is symmetric, in the sense that we can go to the opposite direction, and it's going to be a valid depth first search as well. In the first slide, we went to the left. In this situation, we can implement depth first search that we visit the right child first. So we're standing at the root node and we keep visiting the right subtree. Then okay, G doesn't have any right subtree, so it's going to visit the left subtree. Then we backtrack to G, then we backtrack to A, and then we visit its second child, the F. It doesn't have any children, so we backtrack to A, and lately we visit the left child, the B, then the right child of B, which is the D, then the E, and then at last the C. So basically we can go to the left and we can go to the right, it doesn't matter. But if we start implementing that we go to the left, that we have to be consistent and we have to go to the left as far as possible. If we decide that we go to the right, we implement our depth first search like that. It's okay, it's going to be a valid depth first search implementation, but we have to be consistent. We have to go to the right whenever it's possible. We can't vary that first we go to the right, then we go to the left. I mean that we visit the right subtree, then the left subtree. We have to be consistent. But it doesn't matter whether we go to the left subtree or the right subtree, it's going to be a valid depth-first search implementation. So basically that's all about depth-first search. Thanks for watching.